Hello everyone, welcome back to Discrete Mathematics and its applications, and we are still in the topic of partial ordering, specifically on least, greatest, minimal, and maximal elements. We've seen definition and some examples of the notion of least, greatest, minimal, and maximal elements. Now I ask you to solve these exercises. If you're done, then we shall discuss the solutions, but otherwise pause the video and try solving this first. So let's start with the first one. So give, if any, the least, greatest, minimal, and maximal elements of the poset 2 to the power of s for any set S. Remember, 2 to the power of s is the power set of S, so the set of all subsets of S. So we don't know S here. So we've seen this poset for a particular example of a set S, but because S is not explicitly given, then S can be any set here. So what is the least element of the set? So the least element, right? The set A such that A is a subset of B for all B in the power set, right? So, and the only set that satisfies this is actually A is empty set. So this is the least element. How about the greatest element? Do we have a greatest element? Well, let's see. Is there a set A such that B is a subset of A for all set B in the power set? So that means, what is the set that is both a subset of S and superset of every other subset of S? So the only set that satisfies this is when A is actually the set S. So this is the empty set is the least element, and the set S itself is the greatest element of this poset. Yeah. Now, how about the minimal and maximal? Well, a minimal element is clear because the empty set is the minimal element, because no other set B in the power set with B subset of empty set. Sorry, associate strict subset of empty set. Similarly, the maximal element is actually S. Yeah. Now, that's the first question. So now, what about the second? Now we have a finite set. This time we need to draw the Hasse diagram because we have a finite set here, and the relation is divisibility relation. So we would have 2 here, 4, and then 5, let me just erase this a little bit. So 2, 4, and then 5, and then 10. So 2 divides 10, and it's also 5 divides 10, and you have 12. So 4 divides 12, and then 20, 10 divides 20, and then 20 is here, then 25, 5 divided 75. So the least element is none because there is no element that is less than or equal to every other element in the set. Greatest element is also none, so there is no element that is greater than or equal to every other element in the set. You see, there is no all-encompassing here. So you have, if it has a greatest element, it has to put your position here, right? So there is no greatest element. And how about minimal element? So this is pretty clear. The minimal elements are 2 and 5, and whereas the maximal elements, this is the maximal elements, are 12, 20, and 25. Yeah. So that's the second question. So now how about the third one? Now this is an infinite set. Set of positive integers. So z plus is 1, 2, 3, and so on, right? We want to have a divisibility relation as the partial order, right? So we could try drawing some part of the poset, part of the Hasse diagram. Clearly 1 is below because 1 divides every other elements, right? So 2, 3, 4, 5, for example, but 4 of course is not here. 4 must be here, right? Yeah. So, and maybe here is 7. Yeah, 6 must be here. 5, and then 7, and then 8 must be here. 9 is here. 10 is here, and so on, right? So you have many of them. So clearly this element is 1 because, well, because of course 1 divides A for all A positive integers. Yeah. Now how about greatest element? Well, you see greatest element, you don't have a greatest element here because whenever you have one element, then there will be another none, right? So there will be another element above it, right? So for example, yeah, why? So because if x is the greatest element, I should probably write it, because if x is an integer, yeah, for example 2x is also an integer, and x divides 2x, right? So 2x is above x. Yeah. So for every element, you always have an element above it. So that element x cannot be the greatest, yeah, because it has because it is not greater than or equal to every other element. Similarly, also minimal element here. Minimal element is 1, and maximal element is also none. So there is no maximal element. Yeah. With the same reason here. Yeah. So that's the answer of the third question. Now how about the fourth questions? What is an example of an infinite pose set that has a greatest and least element? Now this is interesting question. So I'll give you an example. The pose set is actually 2 to the power of n. Yeah, that is a power set of the natural numbers, and the relation is subset. Yeah, so here the least element is, again, it's an empty set, because empty set is subset of, so just to clarify, subset of the set of any set of natural numbers. So let me just clarify this first. So this 2 to the power of n, it consists of the empty set of, for example, 1, maybe 1, 2, or 3, 4, 5, any set of natural numbers. Yeah, so this is the power set, so any subset of natural numbers are in 2 to the power of n. So the least element is the empty set, because empty set is subset of every other element. And then the greatest element is the set of natural number itself. Yeah, because all set A in here satisfies A as a subset of the, yeah, and clearly this is infinite, right? Infinite. So we have an infinite pose set with the greatest and least element. So this is one, right? And I'll give another example. So for example, the set of real numbers such that 0 is less than or equal to x, real number x at 0 is less than or equal to x, less than or equal to 1, and the relation is well, say simply, for example, this one here, the least element is clearly 0, and the greatest element is clearly 1, and of course this is infinite. Yeah, so you have 2 examples for this question. We have many more examples, of course, right? You could imagine other examples to answer this question. Now, for the final question in the exercise, you are asked to show that the greatest element of a pose set is unique if it exists. So what does it mean? It means that let S comma this be a pose set, and say X is a greatest element. Or I should say, to go a bit more direct, suppose we have a pose set and X and Y are greatest elements of the pose set with X different from Y. So if this is the case, yeah, then by definition X is x is less than or equal to y because y is a greatest element. Yeah. Also, y must be less than or equal to x because x is a greatest element. Right? But the relation in partial order is antisymmetric. So because the relation is antisymmetric, this implies, so we have x is actually equal to y. Yeah. So this cannot hold, right? Yeah. So this is the demonstration that if you have two greatest elements and they have to be equal. Yeah. So that means the greatest element of a both set is unique. So that's why we call it the greatest element. So we stop here and we shall continue with the next topic, subtopic on partial order in the next video.